This video is going to discuss the chain rule, which is really one of our most important derivative rules. The chain rule allows us to work with compositions of functions. I'm going to start by just giving you a physical example to try to explain where the chain rule is coming from. So imagine you have a hot air balloon rising in the sky. We could say that its height is a function of time. The height of the balloon varies with time. And so let's just make up some numbers. We could say dh dt is 5 feet per second. That means the balloon is rising at a rate of 5 feet per second. The heights are increasing at that rate. Now, at the same time, the air temperature might be changing as we go up. The air temperature might be decreasing as we go up. So temperature, which I'm going to call big T, is actually a function of the height. So temperature might be a function of height. And let's just imagine, again, I'm just making up numbers here, that as we go up, our temperature is decreasing at a rate of 0.1 degrees Fahrenheit per foot. So that's dt dh, how temperature is changing with height. Now, we may want to know how is the temperature changing with respect to time for someone who's on that hot air balloon. Or in other words, what is dt, d temperature, d time, d big T, d little t. And so in this problem, we technically have a composition of functions. Temperature depends on height, and height depends on time. Well, if we want to find this derivative, we have to multiply the 5 feet per second, so we're going up at a rate of 5 feet per second, and then as we go up, the temperature is going down by 0.1 degrees Fahrenheit per foot. And so if we multiply those two numbers together, that should give me my rate of change. That tells me if I'm sitting on that hot air balloon, I expect the temperature to decrease by 0.5 degree per second. And so what we've done here is we've taken our dt dh and multiplied it by dh dt. We've taken the derivative of our outside function times the derivative of our inside function. And so that is an example of how the chain rule works. Now, more formally, or using function notation, we can say that if we have a composition of functions, so f is a function of u, which is a function of x, the chain rule says if I want to take the derivative of this composition with respect to x, I'm going to take the derivative of my outside function, so I'm going to take f prime of u, and I'm going to multiply that by the derivative of my inside function, which u prime of x. Now, I think this will be a lot easier for me to explain by just doing an example. So I want to just dive into examples right away. So let's say we have the function f of x equals 4 times 3x plus 5 to the third. This is a composition in that I have something cubed, and it's not just an x cubed. It's something more complicated being cubed. So we can say that our inside function is u equals 3x plus 5. Then my outside function, if u is 3x plus 5, then f of u is 4 times u to the third. And so I can find the derivative of u prime, is just 3. Derivative of 3x plus 5 is 3. And my outside derivative, f prime, bring down the 3, I get 12u squared. And so the chain rule says we should multiply these two derivatives together to get our final answer. The derivative of the inside, which is 3, times the derivative of the outside function, which is 12u squared. And so that's 36u squared. And then finally, I do want my final answer to be in terms of x and not u. So I'm going to take this 3x plus 5 and plug that in for u. And my final answer is 36 times 3x plus 5 squared. So that's an example of how the chain rule works. Now, when I do the chain rule, I don't always write down the u's And in fact, when the problems start to get more complicated, sometimes writing those u's down actually makes the problem a little bit harder for me. So I want to show you another way that you can do your work. I don't care how you write out your work, but I just want to show you another way that you can think about this. So exact same problem, f of x equals 4, 3x plus 5 to the third. So when I look at this 3x plus 5, that's my inside function, so I'm kind of ignoring it right now, and I'm just focusing on the cubed. That's the outside operation. To take the derivative of a cubed, I'm going to bring it down, and so 4 times 3 is 12, and then the exponent is going to go down by 1 and turn into a 2. So derivative of a cubed, bring down the 3, exponent becomes a 2. And then I'm going to keep this 3x plus 5 as is. I'm not going to change that. And so what I have written down is my outer function derivative. And then the chain rule says I have to multiply by the derivative of what's inside. 3x plus 5 is inside, so derivative of 3x plus 5 is just 3. And 12 times 3 is 36. And there's my answer. F prime is 36 times 3x plus 5 squared. All right, let's do a couple more examples. So let's consider the function f of x equals square root of cosine x. Let's find the derivative. So first thing I'm going to do is change that square root to a 1/2 power. So this is the same as f of x equal cosine x raised to the 1/2 power. We could say that our inside function, our u, is cosine x, and our outside function is u to the 1/2. We have cosine x to the 1/2. The derivative of cosine x is negative sine x, and the derivative of u to the 1/2 would be 1/2 u to the negative 1/2. Chain rule says I have to multiply those two derivatives together. So negative sine x times 1/2 u to the negative 1/2. And then I'm going to replace that u with the cosine x. So negative 1/2 sine x, cosine x to the negative 1/2. And then finally, I'll clean up that answer a little bit. Cosine to the negative 1/2, I can bring that to the bottom. So I just put it next to that 2 in the 1/2. And cosine to the 1/2 becomes a square root of cosine x. So we could write this answer as negative 1 sine x divided by 2 square root of cosine x. All right, let me show you this problem without writing down the u's. So same problem, we've got cosine x raised to the 1/2. So another way we could write this out is my outside function is that 1/2 power. So to take the derivative of the 1/2 power, I bring it down and I get 1/2, and then the exponent becomes negative 1/2. I did 1/2 minus 1. The cosine x stays the same. I haven't dealt with that yet. So my outside derivative is 1/2 cosine x to the negative 1/2. Then I have to multiply by the derivative of the inside. Inside the parentheses is a cosine x. Derivative of cosine x is negative sine x. And this is going to give me the exact same answer. I've got a negative sine x on the top, a 2 cosine x to the 1/2 on the bottom. We could write that as negative sine x divided by 2 square root cosine x. All right, let's do another one. So I'm just going to keep doing practice. This is an important rule. I promise if you do more practice, it will eventually start to click. So I've got the function f of x equals 5 divided by 2x to the 4th plus 4x. Now, if I wanted to, I could do this problem using the quotient rule. There would be nothing wrong with that. I definitely could use a quotient rule. But we can actually rewrite this as 5 times that denominator, 2x to the 4th plus 4x to the negative 1. And when I rewrite it in this form, this is now a chain rule problem. To find my outside derivative, I bring the negative 1 down. That gives me a negative 5, and the exponent becomes a negative 2. Minus 1 is minus 2. So now I've got negative 5 2x to the fourth plus 4x raised to the negative 2. And then I'm going to multiply that by the derivative of the inside. So the derivative of 2x to the fourth would be 8x to the third, and then plus derivative of 4x is 4. So outside derivative times inside derivative. I'm going to rewrite this. I'm just going to take that 2x to the fourth plus 4x to the negative 2, and I'm going to bring that down to the bottom. Oh, there we go. I'm going to bring that down to the bottom, make the exponent positive. So final answer, negative 5 times 8x to the third plus 4 divided by 2x to the fourth plus 4x quantity squared. All right, let's do another one. Let's take a look at f of x equals sine to the third of 3x plus 2. So when you see that exponent right next to a trig function, that sine to the third, what that actually means is we're taking sine of 3x plus 2, that entire expression, and we're raising that to the third power. So I'm going to rewrite the problem. We've got sine of 3x plus 2, and we're raising that to the third power. This is actually a double chain rule problem. The chain rule works if you have compositions of multiple functions. You just keep multiplying by the derivative of what's inside. So let me show you what I mean by that. The outermost function here is that 3. We have something cubed. So to deal with that, I bring down the 3, and the exponent's going to become a 2. So when we have something cubed, we bring down the 3, exponent becomes a 2. So I've got 3 sine of 3x plus 2. Notice I didn't change the sine of 3x plus 2. That I only do one thing at a time, and all I'm dealing with is the 3. So 3 times sine of 3x plus 2 squared. Inside that exponent, the next function nested in there that I see is the sine. So we have sine of something. The derivative of sine is cosine. So I'm going to get cosine of 3x plus 2. Again, I don't change the 3x plus 2. You're just doing one derivative at a time. And then finally, inside the sine is the 3x plus 2, and the derivative of 3x plus 2 is 3. So all of this together is my answer. There's not much we can do to simplify. I'll multiply the 3 times 3, and that gives me 9. So now I've got 9 sine squared of 3x plus 2 times cosine of 3x plus 2. Let's do one more example. I have the function f of x equals 4x to the third times tangent of square root of x. Let's find the derivative. So this problem is a product, 4x to the third times tangent of square root of x. Tangent of square root of x, that's not a product, that's a composition. The square root of x is inside the tangent function. So we're going to have to use a combination of the product rule and the chain rule. First of all, though, we have a product, the 4x to the third and the tangent of x to the 1/2. I just changed that square root of x to x to the 1/2. Those are being multiplied together. So f prime, derivative of 4x to the third, is 12x squared. And for g prime, here's where I'm going to have to use the chain rule. The derivative of tangent is my outside function, is secant squared. So tangent of x to the 1/2, I'm going to get secant squared of x to the 1/2. The inside function is x to the 1/2, and the derivative of x to the 1/2 would be 1/2 x to the negative 1/2. So I use the chain rule to get my g prime, and then I'm going to put this together into my product rule. So I have to take f prime times g, so 12x squared times tangent of x to the 1/2, plus g prime times f. Let's see, so g prime times f, I'll write that as 1/2 x to the negative 1/2, secant squared of x to the 1/2, and then times f, which is 4x to the third. We can clean this up a little bit. F prime of x is going to be 12x squared, and then I'll just rewrite that as tangent of square root of x, plus 1/2 times 4 is 2, and then x to the negative 1/2 times x to the third, add the exponents. That's going to be x to the 5/2, and then secant squared square root of x. And there's my answer. So that was my last example in this video. The chain rule is a really important derivative rule. We're going to be using it over and over again in this class. If you continue with math, chain rule is going to continue to be important. So please let me know if anything in this video is unclear.